Okay, so this is the last lecture in this series on scaling, and this will be the, I think, most exciting application to statistics. So before all this, we've been just studying problems in scaling. Though if we haven't mentioned that they show up in mathematics and linear algebra, there's a bunch of nice quantities that show up. This is another example of that. This is a really natural application of scaling where we didn't have to do anything like analyzing scaling algorithms exactly analyzes some important problem in statistics. So the problem we're going to study, it's going to be this problem called the matrix and tensor normal model. It's an estimation problem. So first I'm going to go over some background of what are estimation problems and how do we measure how good an estimator is, like what's the goal of these statistical problems. Then I'll give the exact problem that we're going to study, which is the tensor and matrix normal model. And then I'll just mention the main results. It should be pretty clear what the main results are because it'll look a lot like tensor scaling that we studied last time. So we just have to use our recently given results on tensor scaling to give whatever the application will be. Okay. And so what is statistical estimation, right? Statistical estimation is you're given samples from some unknown distribution, D, let's say, and you want to estimate some property of D, right? Maybe the mean, maybe the variance, maybe who knows, right? So you're given a bunch of samples and you want to estimate some concrete quantity. And what are the problems usually? They're defined by a model. So a model is a family of distributions. This should be the opposite. Right, so it's a family of distributions containing your unknown distribution D that it could come from. So given one of these distributions is the true distribution, guess which one it is, or guess some property of it, right? And so some simple examples. Let's say you're given a bunch of 0-1 variables from a biased coin flip, and you want to guess the bias. So you want to guess the probability of the thing landing heads, right? So one very natural estimator is just to output the sample mean, right? It's very natural and it's like hard to even consider what else you could estimate with, right? This is sort of the most natural and only estimator you could think of. But notice now we want to measure something like how far is P hat from P, right? Similarly, and this will be a really important running example for the rest of the talk, right? Let's say you're given a bunch of samples from an unknown Gaussian distribution. This theta inverse will be just for some normalization purposes later. And you want to estimate theta, right? And once again, there's only sort of one thing you could think of, right? So you have a bunch of things, you want to estimate something related to the variance, so you output your sample covariance matrix, right? And then again, you can ask how far will theta hat be from theta, and what's the right way to measure error, right? Keep this one in mind, this one will be showing up a lot, but I'll mention again, what are the two things that we studied here, right? So we're given samples from an unknown distribution, and that distribution comes from a family of distributions, that family you know, right? So in the first example, it was some Bernoulli distribution, and the second example was some Gaussian distribution, and it was a centered Gaussian distribution. So the model in this case is like, what are the set of distributions it could be? And you want to output some property of the distribution that is close to the right thing. So before we gave these two kind of natural estimators, here we'll study a paradigm for how to do statistical estimation. It's called maximum likelihood estimation. So we'll do it in the example of the Gaussian covariance estimation problem, right? So let's say that your guess was theta and you got some sample X, right? So if you got the sample, what's the likelihood that you saw this sample is exactly the PDF at this point, right? So if the PDF is small at this point, it's very unlikely that you saw the sample given that the true distribution was theta, right? And then with that intuition in mind, if you have a bunch of samples and you don't know what the true distribution is, you can measure the likelihood that it was some from this true distribution and then output the guess that gives you the maximum likelihood, right? So remember, the likelihood is if this was a true distribution, what's the probability of seeing your samples? And you can optimize over all the possibilities and say, this is the true distribution that I was most likely to have based on my samples. Cool. And in this Gaussian setting, with some simple transformations, actually what we're doing is optimizing this function right here. The simple transformation is just you take the log. Why do you take the log? It's pretty common in statistical estimation because when you have a bunch of independent samples and you take the log of the PDF, right, it breaks up into a sum. So it's easier to handle. But if you take the log and you do some simple transformations, this is the function that you want to minimize now. So minimizing this function is exactly the same as maximizing the likelihood function. And you want to find the theta that minimizes this function. This should remind you a little bit of the scaling problems we did, but I will give another problem that should remind you even more of the scaling problems we did later. But how do we minimize this function? If we can minimize the function, we have something called the maximum likelihood estimator. And then we also want to say that the maximum likelihood estimator is a good estimator. So that's what we'll do next, right? Before we do that, remember the estimator we gave last time was the inverse covariance, right? And it seemed really natural from that perspective. It's also really natural from this perspective. Turns out if you take the gradient of this function of f, the critical point, the point where the gradient is 0, is exactly the inverse covariance. And you can even show that this is the global optimizer. So the global optimizer was the natural guess that we gave earlier. Cool. So sometimes it will be clear what estimator to give, and then sometimes it won't be clear, and then the maximum likelihood estimator is a good idea to start with just to see what the ideas are. So now that we have this estimator, how do we measure how good of an estimator it is? Like, why should we take the maximum likelihood approach? And in this part, we'll mention using some Gaussian concentration that it's a good estimator. And how do we measure good? This is a notion of relative error that we're going to use, right? So for any two possible covariance matrices, let's say, or possible precision matrices, the inverse covariance matrices, we measure the distance by this error function. So either the Frobenius norm or the operator norm of these things. This should look kind of familiar based on the geodesics we've been studying, but I'll give some intuition for where they come from. It's an asymmetric measure, and it sort of tells you some sort of multiplicative error, right? So if the eigenvalues of B, let's say, are small in some direction, then you want to like measure it well in that direction. Or if they're large in that direction, you want to be close multiplicatively. So if the eigenvalues of B are small, you're allowed to make a smaller error. You want a relative error. One example of this is, for example, if the relative operator norm error is at most epsilon, then every quadratic form is multiplicatively approximated by 1 plus minus epsilon. This kind of approximation shows up a lot in Laplacian solvers and graph sparsification, these kind of spectral sparsification ideas, and in numerical linear algebra, actually. Another nice intuition that should be helpful from the perspective of scaling that we're already studying is that it's natural from our geodesic perspective. So recall that the geodesics involved going along the exponentials of these curves, right? So e to the tx, where x is the log of something, right? And turns out by Taylor approximation, when x is small, by Taylor approximation, this relative error exactly is up to some constants, just the Frobenius norm of the log. So like, how do we move between positive definite matrices in this geodesic sense is you like take this curve parameterized by x, and then that parameter x is exactly the relative error. That's what we're studying. So when we're going to study all these problems, it's helpful to study the geodesic distance for these problems, right? They'll give nice error bounds exactly for the relative error distance that people care about in statistics anyway. Cool. Now there's two important properties of the setup that we have so far, and that'll make our analysis quite a bit easier, right? So the important properties are, first, the MLE was an optimization problem. Turns out the optimization problem is invariant under these linear transformations. So let's say you have these samples from the identity Gaussian, and then you have another set of samples, which are sampled from A star A, right? So this is just a general covariance matrix. It might be easier to understand how the MLE behaves for the identity. It's like the most normalized. It might be easier to reduce to that setting. And turns out there is a nice way to do it. I won't really go into too much of this calculation, but there's a really simple invariance property that comes out for the function that we're optimizing, right? So that means that the optimizer of these two functions is very strongly related. So the MLE for the identity case and the MLE for an arbitrary covariance case is related by just exactly these simple linear transformations. And the other thing is that the error measure that we're studying is also invariant under the same linear transformations, right? So what that means is you have some arbitrary unknown covariance matrix, but it's generated by first sampling a standard Gaussian and then hitting it with some linear transform, right? You could just for the analysis sake, undo that linear transform, and everything should stay the same. Like both the MLEs will stay the same and the error, relative error will stay the same. So that means that you could just analyze the setting when the true covariance matrix is the identity, and you'll learn what the MLE behavior is in all cases, right? That'll make lots of concentration properties a lot nicer, and it'll make our analysis quite a bit easier. So we're going to use this invariance here and also in the tensor problem that we're going to study later. So now all that's left, now that we've done this reduction, is to do the analysis. And since we're studying the case of standard Gaussians, we have like really powerful Gaussian concentration inequalities that we can use. So the sample covariance of a bunch of Gaussians, a bunch of standard Gaussians, concentrates super well around the actual covariance, right? So as soon as you get n much bigger than d, right, you have relative error that's very, very good. And in particular, just this concentration enough alone gives that the MLE, which is the inverse sample covariance, in order to get epsilon relative error in either the operator norm or in the Frobenius norm, you just need n more than d over epsilon squared samples. Right below, I rewrote this a little bit. I think this gives some intuition for where these quantities come from, right? So remember that n is the number of samples, and the samples are d-dimensional vectors, right? So nd is sort of the like number of linear constraints you're learning from getting the samples. And on this side is d squared. D squared is the number of degrees of freedom that the unknown covariance has, right? So before you learn d squared constraints, there's really nothing you can say yet, right? If you haven't even learned, there's like whole dimensions that you're missing if you haven't even learned d squared constraints. But once you have, then turns out that the error does almost as well as you like 1 over epsilon squared convergence after that. This is the kind of analysis that we'd want for our more general problems. So like the sample complexity should be as close as possible to when it's possible to learn something, right? Cool. So keeping that in mind, we'll study our more general problem called a matrix and tensor normal model. So as I mentioned before, right? So this, for any d-dimensional Gaussian, now it's a capital D, right? If you want to learn an arbitrary covariance matrix, right, then you need at least D samples, capital D samples. But now what if your input was some sort of tensor? So like a K part tensor, right? So the dimension of this thing grows as little d to the K, right? So let's say dA equals dm equals d, right? Then if you have m parts, then capital D is d to the m, right? This could be much bigger than any number of samples you could hope for, right? So you can't learn an arbitrary tensor covariance matrix with few samples, but we could change the model and then hope to learn much quicker. That's the plan for the matrix and tensor normal model. So here you have a tensor data, and your covariance also respects this tensor structure, right? So your covariance is theta 1 is a positive definite matrix on the first part, and theta 2 is a positive definite matrix on the second part. So it's a covariance matrix that has a bunch of tensor factors. And the goal of the estimation for the tensor normal model is now not just to output something that's close to the original covariance matrix, but I want something that's close to each factor, right? So I want to learn something about the factors themselves. So going back to the matrix scaling setting, right? So you want to learn something about, for example, like the row sums and the column sums or something, like some mean for each of the factors that you're getting from. Failing that, we can just learn about the whole covariance matrix, but you still have to output something that's feasible, right? So you still have to output something that's of the form theta a hat. Right, so you can't just output an arbitrary covariance matrix. You have to find a covariance matrix that's made of these tensor factors. And now, what's the best case scenario we can hope for? We can do the same degrees of freedom analysis, right? So if there are m matrices, each dA by dA, right? How many degrees of freedom do they have? They have sum of a dA squared, right? And again, you're getting little n samples. And now it's a much larger space. It's a capital D dimensional space, right? So you hope that once you learn enough constraints to get rid of the degrees of freedom, then you can get a good estimator. So this is the best case scenario. We won't really exactly achieve this, but we'll be pretty close. And so what are our main results? So given samples from the tensor normal model, right? As soon as epsilon is bigger than, remember in the Gaussian case, this was as soon as epsilon is smaller than some constant, then ND bigger than the degrees of freedom over that epsilon squared is enough to get what you want. Here, we have epsilon squared is bigger than some dimension dependent factor, but it's weakly dimension dependent. It's not 1 over product of D, it's just 1 over sum of D, right? So now as soon as epsilon is this small, you get exactly the convergence that you want. So recall that for the Gaussian case, we had D for Gaussian. So if there's only one tensor factor, right? When ND is greater than. So as soon as you had D squared over epsilon squared, or as soon as you got 1 over epsilon squared as many as the degrees of freedom, then you already got Frobenius norm error D times epsilon squared. In fact, in the Gaussian case, we were able to show something stronger, which is the operator norm relative error. Here, we won't be able to do that in this presentation. If you want to see the full results, there's a paper that we've written on these results, which we get some improvements, but it's not as clean as the Gaussian case. So there is still some work to be done. But the point is that one polynomial factor away from the exact thing that you'd hope for in just the Gaussian case, you get Frobenius norm relative error, and you actually output factors. So you've learned something about these factors. And how do we solve this problem? What is the estimator that we gave? It's actually the maximum likelihood estimator. So it's not immediately clear what is the right estimator to do in the tensor normal model, right? It's clear what to do in the Gaussian case, just there's only one thing to do, which is the sample covariance. Turns out that the maximum likelihood estimator is a well-studied estimator that people try to show it exists and try to show it's close before. It turns out that the maximum likelihood estimator, again, remember it's an optimization problem. It's actually the same optimization problem, right? But now you have these tensor vectors. And so the optimization problem that comes out is exactly this problem. These are just 2 forms for it. But importantly, this element should remind you of tensor scaling, right? So this is exactly the operator that we defined for a tuple of tensors. And we're trying to do some sort of norm minimization, right? So we're trying to minimize this thing over all positive definite matrices, which is sort of like minimizing the norm of some scalings of a tensor. So this should remind you really strongly of tensor scaling. And that's because it is almost exactly tensor scaling. There's just a few transformations you have to make, and you can learn exactly what you want about this thing. And so for the Gaussian case, it was clear what the optimizer is. Here, it's not clear how to do the optimization, but now that we've studied tensor scaling, it is clear, right? So now that we've studied tensor scaling, we know the right way to optimize this function is using geodesic convex optimization, because this is very related to the Kempness function from tensor scaling. And that was geodesically convex, meaning that the minimizer can be found by doing some natural algorithms, right? And even better, in the statistical community, people have already studied this thing called the flip-flop algorithm. Before I even say it, you could probably guess what it does. It's exactly just a generalization of the Sinkhorn scaling algorithm. So there's many tensor parts, right? We just fix one at a time, and we keep fixing the worst error. So what does that mean? We're trying to make, we want rho x of A to be equal to 1 over. So this is what we want. We just normalize to make that happen, right? And turns out that because we've studied Sinkhorn scaling for matrix scaling, you could believe that this flip-flop algorithm is some sort of descent method on the convex formulation that we've given, right? So there's a GS convex formulation, and this is some sort of descent method. And so for the same reasons as before, using the strongly convex analysis, as we'll show later, for the same reasons as before, as soon as you can get the strong bound on the optimizer, this flip-flop algorithm actually converges to the optimizer very quickly, right? So as soon as you have enough samples, in order to get delta error, you only need log 1 over delta iterations of flip-flop. Whereas at the original convex formulation for matrix scaling, you needed 1 over delta type of convergence, right? Cool. So both these results will follow pretty simply from generalizing the algorithmic analysis of matrix scaling to tensor scaling. And what's our proof strategy? Well, based on what we've seen so far, is we have a nice analysis of tensor scaling when the input is strongly convex and the error is small, right? So we want to study random inputs. That's the game we have, because our inputs, as we mentioned, we can reduce by linear invariance. We can reduce the case when you just have identity covariance, right? So recall that that's because, again, the MLE and the relative error measure are invariant in the same way. So you could just study when the input comes from a standard Gaussian. And then Gaussian concentration for Gaussian covariance estimation showed that estimator, which was the sample covariance, that thing was close to the right thing almost always, right? So similarly, it turns out the geodesic gradient, as we studied in the tensor scaling problem, is exactly the distance from your operator to the identity, right? And Gaussian concentration, since X is a bunch of Gaussians, this tells you that the sample covariance is very close to the true covariance. So it tells you that the geodesic gradient is small with high probability, right? And the only thing remaining to show strong convexity was that spectral condition that we defined in the tensor scaling presentation, right? So the spectral condition I can recall was you want so remember that this came from the cross term of the Hessian, right? So the cross term was these bipartite marginals inner product with this off diagonal part, and you wanted to show that this is at most lambda, some lambda times the thing you'd expect. And these are all normalization factors that make it work out such that once you have lambda to be smaller than a constant, and if you have epsilon to be smaller than a constant, then you'll get very strong convexity right away. Cool. So the important point was we needed to show strong convexity and small gradient. Small gradient was accomplished by sort of standard Gaussian concentration. The spectral condition is occurs because of a really nice result by Pizier. He used this nice trace method to think of this as a some sort of quantum expansion property. So in the same way that people have proved, for example, that random deregular graphs are expanders, Pizier has some similar ideas to show that random Gaussian inputs for this quantum map give you some sort of quantum expansion. And it's almost optimal the amount of quantum expansion he has. So we were able to rely on that theorem to give the spectral condition that we wanted. And then that immediately gave us strong convexity, right? And so now we have strong convexity. We can apply the strongly convex analysis from tensor scaling that we talked about last time. And that showed that the optimizer is very close by. And further, we have this robustness of strong convexity, right? So the input is strongly convex, which means the optimizer is also strongly convex because it's close by, which means that all algorithms start converging quickly once they're reached nearby to the optimizer, right? So that was the final step. The first theorem showed that the MLE is close because the optimizer is close by. The second theorem showed that the flip-flop algorithm converges the MLE because the optimizer is strongly convex. Cool. And how do we prove that? This is just a simple generalization of the matrix scaling problem, right? So the same ideas in matrix scaling, we use actual strong convexity. Here we use geodesic strong convexity to talk about when do descent algorithms stay within a level set and converge quickly. But yeah, the key points when this we're only analyzing random inputs. So we can study Gaussian, we can use Gaussian concentration and lots of properties of Gaussians to show that it satisfies the strong convexity that we defined last time. And then we get the strong analysis that we wanted. So to recap on the theorems. Right, so as soon as, oops. Right, so as soon as the number of constraints that you've learned from the samples is some polynomial factor larger than the number of degrees of freedom, then you get epsilon error. So almost exactly what you get for the Gaussian. And this reduces exactly to tensor scaling. Cool. So that'll be the result.
Okay. Cool. Thank you very much.